Long ago, the appearance of the Aurora Borealis caused a range of emotions in the people who witnessed them. Alarm, fear, wonder, dread, and excitement, to name a few. People did not understand what caused them, or this amazing spectacle of the sky.
The phenomena of the aurora was explained by different stories. People thought the lights were gods or goddesses appearing to mortals, spirits or souls dancing in the sky.
The red color was associated with legends or myth relating to blood, murder, death, wars, and suicide.
Pierre Gassendi, a French astronomer, was the person who came up with the name Aurora Borealis. Aurora is for the goddess of dawns, whose name was Aurora, and Borealis for the god of the north wind, whose name is Boreas in Latin.
Gassendi was born in France, and after studying in Aix and Paris, he got a doctorate in theology. A year later, he was ordained and appointed to the chair of philosophy at Aix. As an astronomer, he made multiple observations of comets, eclipses, and celestial phenomena such as the Aurora Borealis.
Aurora is a luminous glow of the upper atmosphere, which is caused by energetic particles that enter the atmosphere from above.
This definition differentiates aurora from other forms of airglow and from sky brightness that is due to reflected or scattered sunlight. Airglow features that have internal energy sources are more common than aurora. For example, lightning and all associated optical emissions, like sprites, should not be considered aurora.
On Earth, the energetic particles that make aurora come from geospace environment, which is the magnetosphere.
The electrons travel along magnetic field lines. The Earth's magnetic field looks like that of a dipole magnet, where the field lines are coming out and going into the Earth near the poles. The auroral electrons are thus guided to the high latitude atmosphere. As they penetrate into the upper atmosphere, the chance of colliding with an atom or molecule increases the deeper they go.
Once a collision takes place, the atom or molecules take some of the energy, or the energetic particle, and stores it as internal energy, while the electron goes on with a reduced speed. The process of storing energy in a molecule or atom is called exciting the atom. An excited atom or molecule can return to the non-excited state or ground state by sending off a proton by making light.
There is an aurora at both the northern and southern poles on Earth. They are both very similar, besides the fact that it is only during the fall and spring that a person can see the aurora in Antarctica.
The sun has many magnetic fields that emerge from within the sun, forming loops that protrude out from the surface. As the sun rotates, these magnetic fields get distorted, twisted, and knocked together, where they burst and a sunspot is made.
They usually appear in pairs and can vary in size, the largest being several times the diameter of Earth. These sunspot portals are responsible for the solar wind projections. The solar wind travels at a speed covering 93 million miles to Earth in about 2 to 3 days. It's around 1,000 kilometers per second or 1 million miles per hour.
Normally, the Earth can deflect such space matter easily because of Earth's magnetic field, which acts as a protective shield. However, in high-activity cycles called solar flares, the increased particles travel through space and bombard our magnetic shield to deform it slightly in shape.
Some of these particles penetrate our magnetic field and come into contact with different gases, which produce the aurora northern lights that we see.
When an excited atom or molecule returns to the ground state, it sends a photon with a specific energy. This energy depends on the type of atom and on the level of excitement, and we perceive the energy of a photon as color.
The upper atmosphere consists of air just like the air we breathe. At very high altitudes, there is atomic oxygen in addition to normal air, which is made up of molecular nitrogen and molecular oxygen. The energetic electrons in Aurora are strong enough to occasionally split the molecules of the air into nitrogen and oxygen atoms.
The photons that come out of Aurora have therefore the signature colors of nitrogen and oxygen molecules and atoms. Oxygen atoms, for example, strongly emit photons in two typical colors, green and red. The red is a brownish red that is at the limit of what the human eye can see. And although the red auroral emission is often very bright, we can barely see it.
When we see green light, it's oxygen up to 150 miles in altitude. When we see red light, it's oxygen above 150 miles in altitude. When we see blue light, it's nitrogen up to 60 miles in altitude. And when we see purple light, it's nitrogen above 60 miles in altitude. Yellow-green is the most common color aurora that people see, while red is the least common.
Northern aurora is in the high northern latitudes during the winter, such as Alaska, Canada, and Scandinavia. To see an aurora, you need a clear and dark sky. There is always an aurora somewhere on Earth at any given time.
During very large auroral events, the aurora may be seen throughout the U.S. and Europe, but these events are very rare. In North Dakota, Michigan, Quebec, and central Scandinavia, you might be able to see aurora on the northern horizon when there is more activity.
In the southern hemisphere, the aurora has to be fairly active before it can be seen from places other than Antarctica. The best time to watch for an aurora is around 3 or 4 hours within hours of midnight.
If a planet has an atmosphere and is bombarded by energetic particles, it will have an aurora.
Planets like Venus, which has no magnetic field, have very irregular aurora, while planets like Earth, Jupiter, or Saturn, which have an intrinsic magnetic dipole field, have aurora of oval-shaped crowns of light on both hemispheres.
When the magnetic field of a planet is not aligned with the rotational axis, there may be an auroral oval which might be near the equator, like that on Uranus or Neptune.